Hi, I'm Dr. Robin, aka Double O Pi. In today's video, we're going to use Solver to solve for concentrations in a more complicated system than what we did before. If you haven't seen the previous videos in this series on the systematic treatment of equilibrium, I'll link them down below in the description. You'll need to watch these first so you can understand how to evaluate your system and create a series of equations to solve for the concentrations of everything in that video. In the first Solver video, I walked you through the process of solving for concentrations of a system that contained ionic compounds and weak acids and bases. We used the concentration of H+ as our target unknown for that system because many of the unknown concentrations were related to H+. But when you look through the equations for the systems in this video, you will see some that aren't related to H+ in any way, shape, or form. To solve the system, we're going to need to use two target ions and therefore two base equations, but more on that later. Here's the system. 0.10 molar ammonia and 0.010 molar silver nitrate. It doesn't look that complicated, but let's go through and think about what species would be in this system. Now, this is a system that I talk about in lecture, so I apologize to any of you who aren't in my class. I'm going to go through this next bit very fast. What species we have depends on what reactions that happen in our system. First, let's think about what we get from ionic compound dissociation. Normally, we'd also think about strong acid dissociation at this time, but we don't have any strong acids here. So in this case, it's just going to be silver nitrate dissociating. We're going to end up with Ag+ and nitrate NO3-. Next, from the dissociation of water, we're going to get H+ and OH- as always. Then we have to ask ourselves if we have weak acid or weak base chemistry going on. Of course, we have ammonia, which is a weak base. We'll also therefore have the conjugate acid, ammonium, present in solution. Finally, we have to ask ourselves whether or not we'll have complex formation. To do this, we first identify both possible metals and ligands that might form complexes. Silver is the only possible metal here. Ligands will always be Lewis bases, so we can look at our current list of species to see if any are Lewis bases. We know for sure that ammonia is a base, so we can check out our tables of complex formation constants to see if silver forms complexes with ammonia. The answer is yes, and looking at the table, we can see that silver will form two complexes with ammonia, a complex with one ligand and a complex with two ligands. So there are our two ammonia complexes. But ammonia is not our only Lewis base. Hydroxide also is a Lewis base, so we need to check to see if silver forms hydroxide complexes. Again, we look at our table and we see two entries for silver hydroxide, a complex with one ligand and a complex with two ligands. So again, we have two complexes. Now let's talk about what equations we're going to use to solve for our concentrations. I'm giving you an abbreviated version of this. Normally we'd go through all of the reactions we mentioned earlier before attempting to come up with equations, but I'm going to do all of that at the same time. Let's start with our charge balance equation. We have 5 cations, silver, H+, ammonium, and our two silver ammonium complexes. On the other side of the equation, we have our 3 anions, hydroxide, nitrate, and our second silver hydroxide complex. This is the way we would write this if we were solving it on paper, but we're going to rewrite it for Solver so everything is on one side of the equation. So let's subtract everything on this side from both sides of the equation, and that gives us this equation where everything is equal to 0. Now that's all ready to go into Excel. What other equations are we going to use here? Let's think first about equilibrium constant expressions. The first one is for the dissociation of water. I've rewritten this so it's in the form we like to use when solving with H+ as our target variable. We're also going to have two equations that contain both ammonia and ammonium. The acid dissociation constant expression for ammonium, as well as a mass balance where the total amount of ammonia and ammonium equals 0.10 molar. We got that number from our recipe. However, if you try using these to solve for concentration of these two species in terms of H+, you're going to go through some pretty messy algebra. There's a shortcut that avoids that, so don't use these equations in Excel. The shortcut is to multiply the total concentration from your mass balance by your fractional composition equations. That's what I have here. remember that ammonium is our acid here, so we use the expression for the fractional composition of HA for that. Ammonia is our base, so that's where we use the A- expression. Now let's talk about the equilibrium constants for our complex formation. Be sure to consult your complex formation constant tables, not only to figure out how many constants are formed, but also to get your actual complex formation constants. Don't forget that what's in the tables are the log of beta, so make sure you account for that when you're writing your equilibrium constants. We are going to form 4 complexes, and here are the equilibrium constant expressions for each of them. 2 for the ammonia complexes, and 2 for the hydroxide complexes. Of course, if you look at these equilibrium constants the way they're currently written, they're not in a great form to solve for anything. Let's rewrite them the same way we do when we're solving for complex concentrations on paper, with the concentrations of the complex on one side and everything else on the other. I already mentioned one mass balance for ammonia and ammonium, but we have 2 more mass balances to round out our set of equations. First, we have a mass balance for nitrate. That's pretty easy because nitrate isn't going to do any chemistry. So we're just going to say that NO3- equals 0.010 and call it good. We also have a mass balance for silver. This is a little more complicated because silver can stay as the free silver ion, or it can participate in forming one of our 4 silver complexes. But we know that the total of these concentrations of silver species has to equal 0.010 molar. We're going to transform this one as well because this is going to end up being one of our base equations. So let's subtract the 0.010 from both sides so we end up with an equation with all of this stuff equal to 0. So now let's dive into Excel. As I said earlier, this is going to be different from our previous systems because we'll have 2 target ions, H+ to help us with our acid-base chemistry, but also the free silver ion, which is going to help us solve for our complex concentrations. I'm going to start this the way we always start systematic treatment of equilibrium stuff, which is by making a column for my species and one for my concentrations. I'm also going to make a section over here that's going to be for my constants. For ammonia, I'm going to have my pKa, which is 9.245. Then I'll make a cell for Ka, and I'm going to calculate that from my Ka. That's 10 to the minus pKa. Then I'm going to do my complexes. I'm going to make a column for my log of beta, and then I'm going to make this column beta. For complexes, we're going to have silver with 1 ammonia, which has a log of 2.0. So beta is going to be 10 to the power of log of beta. Next up, we're going to have silver with 2 ammonias. Oh, I forgot to put the charges here. That's a plus, and that's a plus. The log of beta for this one is 4.0. Next, we have our silver hydroxide. Log of beta for that is 3.3. We have our silver with 2 hydroxides and a -1 charge. Log of beta for that complex is 7.2. You'll notice that I didn't put in a formula for beta for these last 3, and that's because the formula is all the same. As you can see right here, it's 10 to the power of the log of beta. Since that's going to be true for all of them, I can just take this cell and drag it down, and now we have all of our beta values. I'm going to put in the species now. H+, OH-, NO3-, NH3, NH4+, Ag+. There are ways to get these things super and subscripted, but I'm way too lazy to do them most of the time. Now let's do our complexes. Ag with NH3+, Ag with 2 NH3s+, and then Ag with 1 hydroxide, and Ag with 2 hydroxides minus. Now let's put in our concentrations. In the last video, I had you fill in a starter concentration for H+, and then later we said, let's make the pH. I'm just going to start directly with pH this time. Normally I start with pH 7 as a default, but because we put in a ton of ammonia, I think this is going to be basic. So I'm going to start at pH 8. Our H+ then is going to be 10 to the negative pH. Our OH minus is going to be 10 to the minus 14th divided by H plus. And again, I'm just going to click on that cell that contains the H plus concentration. We have an actual number for NO3 minus, so I can just enter 0.010 here. For NH3, we have to use the formula we came up with for our total concentration and our fractional composition. So this is going to be 0.10 times Ka, so I'm going to click on our Ka cell. Whoops, classic mistake. It's not letting me click on the cell because I forgot to start with an equals, so it doesn't realize I've tried to write a formula. So equals 0.10 times Ka, so click on the Ka cell divided by, one of the common issues I see is that in our denominator we have something plus something, and if you just type it in that way, because Excel follows the PEMDAS rules, it's going to give you the wrong answer. So make sure you put the denominator in parentheses, and that's H plus Ka. We can do the same thing for NH4 plus. Again, we're going to do our total concentration times our fractional composition, which is H plus divided by H plus Ka. Next we have silver. So as I said before, when we have two kinds of chemistry going on, in this case, that's both weak acid base and complexation chemistry, we're going to need two different target unknowns. Our first one was H plus. Again, we always use that one when we have weak acids and bases. But when you have complexes, you have all of those complex formation constants, which may or may not have any link at all to H plus. What they all are linked to in this case, though, is the free ion of silver, Ag plus. If you have a different metal in your complexes, obviously you'd use that metal instead. So we're using silver as our second target unknown. And we could put a starter number in for silver, but sometimes those concentrations of the free metal ion get really, really small. And of course, silver hates working with really small numbers. So we're going to do something that you've probably never heard of. In fact, I never thought about it until I started doing this problem. And that's PAG, which is the negative log of our silver concentration. So this silver concentration is going to be this. Of course, we didn't put a value in for PAG, so right now Excel thinks our silver concentration is 10 to the 0, or 1 molar, which is way too big. I'm going to put 2 in PAG for now, and the reason I picked that number is that it gives us a starting concentration of 0.01, which is our total concentration of silver. Obviously, this number is going to change after our silver complexes form. Our concentration of free silver will go down. Now let's look at our complex concentrations. So this first one will be equal to beta 1 for ammonia times our free silver concentration times the concentration of ammonia. This one is going to be equal to beta 2 for ammonia times our free silver concentration times the concentration of ammonia squared. This one will equal beta 1 for hydroxide times free silver times hydroxide. And then this last one will equal the beta 2 value for hydroxide times free silver times hydroxide squared. So these are the concentrations that we would have at a pH of 8 and a PAG of 2. But are those the right concentrations? How can we tell? Well, when we were doing a system that only had weak acids and weak bases, we used our charge balance as the base equation to find a good value for our pH. So we're going to start with that because we still have weak acid, weak base things going on in this system. So here's our charge balance space and the equation we came up with down here. So we have silver plus H plus NH4 plus this complex plus this complex minus OH minus NO3 minus this silver hydroxide complex. Now, in an ideal world, this should equal 0. It doesn't, so that should tell us right away that the pH value is not correct. And you can see that if we changed our pH, that's going to change. The other thing we did before is that we looked at the log of the charge balance squared, and that was what we were actually optimizing. So let's do the log of this squared. And again, you can see that we can change our pH, and that will change this value. We want this to get smaller and smaller. So that will help us adjust our pH, but we're trying to optimize two target variables here, and anytime you do that, you're going to need two base equations. You always need one base equation for every target unknown. So what is our second base equation going to be? It's going to be our mass balance equation for silver. If we look at that, we see that it contains all of our silver compounds. Actually, I'm just going to sum up all of these. And then I'm going to subtract 0.010. That should also equal 0. Does it? No. Although at least it's closer than our charge balance. For this, we're also going to do a log of the silver mass balance squared. So now what we're going to do is use solver to make these as small as possible by changing these. But we have a problem, which is that if you go to solver, the objective cell has to be one cell. I can try to put both of these cells in and minimize those by changing variable cells, well, both of these two. Okay, let's try and run it. Here's what I was saying before. The objective cell must be a single cell on the active sheet. So how do we get these two cells to a single cell? Well, we want both of them to be as small as possible. So let's just add them up. If they're both really small, their sum will be really small too. So this is going to be our objective, and this is just this plus this. So now that we've done that, let's go to solver, set our objective cell to be that. Just double checking that I'm doing the minimum, and we're changing these two cells. Now we're going to hit solve. And let's look at our results. Our pH is going to be 7.88. So I was kind of off when I said pH 8. Our P of Ag is bigger than it was before, so our free silver concentration is smaller. But you could see, looking at these concentrations, we have mostly free silver. We have a moderate amount, like, say, order of magnitude, of our silver ammonia complexes. And then we have very, very little of our silver hydroxide complexes. So that's how you solve more complex systems using solver. If you had more than one metal in your system forming complexes, you would probably have to have each metal be its own target variable. As you can imagine, this would get complicated very quickly if you tried doing it on paper or even on Desmos, but it's really not too hard to do using solver. I hope this has helped you become more familiar with using solver to evaluate messy systems. What other questions do you have? Do you want a video of me doing solver on an even messier system? Let me know in the comments below. Thanks for watching, and I look forward to seeing you again soon. Dr. Robin, signing out.